October 19th, 1959, north of Seattle, Washington. A Boeing 707. 8 people, 4 pilots, 1 flight engineer, 1 technical instructor, 1 FAA inspector. No passengers. A training flight. The instructor exceeded his own company's limits. The trainee grabbed the controls and turned them the wrong way. In the recovery, the instructor overcorrected so violently that 3 engines ripped off the wings in midair. 3 Pratt Whitney turbojets, each weighing over 2 tons, falling through the clouds with no airplane attached. What would cause a test pilot to push a brand new aircraft past its limits on a student's very first flight? The answer reaches beyond one man's judgment, into the earliest days of the jet age, when airlines were racing to transition from propellers to turbines, when no flight simulator existed that could replicate a jet's behavior, and when the only way to learn how a new aircraft behaved at its limits was to take it there for real, with people on board. The Boeing 707 was the most advanced commercial aircraft in the world. It was also, in one specific way, slightly unstable. Everyone knew about it. Boeing had a procedure to manage it, but the procedure required turning off the very system designed to keep the instability in check. And on this flight, when the instability was deliberately provoked beyond the published limits, the procedure was all that stood between 8 men and the laws of physics. This is the story of a Boeing 707 training flight that ended in the Stillaguamish River. To understand how it got there, we need to start with the airplane, the airline, and the problem that everyone knew about, but no one had fully solved. In the fall of 1958, the jet age arrived. The Boeing 707 and the Douglas DC-8 entered commercial service within months of each other, and the world of aviation changed overnight. These were faster, smoother, and more capable than anything that had come before, but they were also fundamentally different machines. Swept wings, turbojet engines, flight characteristics that propeller pilots had never encountered. And one of those characteristics had a name that would become infamous among the first generation of jet crews: Dutch roll. Dutch roll is a coupled oscillation in yaw and roll that affects all aircraft but is far more pronounced on swept-wing jets. When the aircraft yaws to one side, the advancing wing generates more lift than the retreating wing, which induces a roll in the same direction. The vertical stabilizer then pushes the nose back the other way, but inertia carries it past center and the cycle repeats. On a well-designed airplane, these oscillations are stable. Each swing is smaller than the last, and the motion dies out on its own. On a less well-designed airplane, the oscillations are divergent. Each swing grows larger, and if nothing stops them, the airplane can be torn apart. The early Boeing 707 fell somewhere in between. Its Dutch roll was slightly divergent, not dramatically so. Each oscillation was only marginally larger than the last, but it would not stop on its own. Left unchecked, it would slowly build until the bank angles exceeded the structural limits of the airframe. To manage this, Boeing equipped the 707 with a yaw damper, a device that makes constant small rudder inputs to suppress any uncommanded yawing before it can develop into a full Dutch roll cycle. But the first-generation yaw damper on the 707 had a problem. Its rudder inputs were transmitted back through the control cables to the pedals in the cockpit. Under normal conditions, this was merely annoying, but during an engine failure, when the pilot needed full rudder authority to counteract asymmetric thrust, the yaw damper fought back. At low speeds with flaps extended, the combined force could exceed what a pilot could physically overcome. For this reason, standard procedure on early 707s was to turn the yaw damper off during takeoff until the flaps were retracted, and again during landing once full flaps were selected. But with the yaw damper off and the flaps extended, the 707 was in its most vulnerable configuration for Dutch roll. The oscillations were divergent, the flaps made them worse, and the pilots were on their own. This meant that every 707 crew had to know how to recognize and recover from Dutch roll manually. And since flight simulators in 1959 were primitive devices that bore little resemblance to the actual aircraft, the only place to practice was in the airplane itself. Braniff International Airways, based in Dallas, Texas, had ordered 5 of the new Boeing 707-220 variant, equipped with more powerful Pratt Whitney JT4A-3 engines for hot and high operations. These would be Braniff's first jets. To prepare, the airline sent several of its most experienced propeller captains to Seattle for transition training conducted by Boeing directly. The pilots completed roughly 160 hours of ground school, learning jet aerodynamics, systems, and procedures. By October, they were ready to fly. On the afternoon of October 19th, 8 men arrived at Boeing Field in Seattle for the first training flight. In the left seat was a 32-year-old Boeing test pilot and instructor named Russell Baum, with about 5,000 total hours, 369 of them on the 707. That was not a great deal of experience for an instructor role on a new aircraft type, but he held all the required qualifications. The right seat was occupied by Captain John Burke, a 49-year-old Braniff captain with an extraordinary 23,563 flying hours, every one of them on propeller aircraft. This was his first time in a jet. Also on board was Captain Frank Staley, 43, another Braniff veteran with 20,450 hours, also all on props. The remaining crew included a Boeing flight engineer, a Braniff flight engineer, a Braniff technical instructor named Fred Simink, a second Boeing pilot, and an FAA air carrier operations inspector, along to observe. The aircraft was N7071, a brand new 707-220, with only 173 hours on it. It had just completed certification, flight testing, and was awaiting final FAA approval. Boeing had authorization to conduct training flights in the interim. The weather was overcast at 4,000 feet, with conditions clear above. An instrument flight plan was filed with a training area defined north of Seattle, and fuel for about 5 hours. All 8 men gathered in the cockpit for the flight. There was no cockpit voice recorder installed. Federal regulations at the time only required a flight recorder for passenger operations, and even that device captured only basic parameters. Much of what happened next would have to be reconstructed from the flight data, the wreckage, and the testimony of the 4 survivors. At 13:30, the 707 took off from Boeing Field and headed north toward the practice area above the overcast. All 8 men crowded into the cockpit to observe. Baum, the Boeing instructor, occupied the left seat with Burke, the Braniff captain, beside him. The training began with basic maneuvers. Baum demonstrated each one first, then coached the trainee through the same exercise. Steep turns, slow flight, configuration changes. The early sequences went smoothly. Burke was a natural pilot with over 23,000 hours of muscle memory. The jet felt different from anything he had flown, faster, smoother, more powerful. But the fundamentals of flight were the same. Then Baum turned off the yaw damper. With the switch off, the 707's natural Dutch roll tendency was now unmasked. No automatic damping, no safety net. If the aircraft started to oscillate, only the pilots could stop it. In a clean configuration at cruise speed, Baum demonstrated the phenomenon. The oscillations were mild, a gentle swaying that was more uncomfortable than dangerous. Burke recovered with coaching, applying aileron against the direction of roll until the wings settled. Standard training for the era. But then Baum did something that narrowed the margins dramatically. He slowed the aircraft to 155 knots and extended the flaps to 40 degrees, the full landing configuration. This was the most vulnerable combination for Dutch roll on the 707. Slower speed meant less airflow over the control surfaces, which meant less roll authority for recovery. Extended flaps amplified the oscillation because they increased the wing area that caught the asymmetric airflow during each yaw swing. And the 707's slightly divergent characteristic meant that in this configuration, each swing would grow, not shrink, with every cycle. To understand why this mattered so much, consider the math of divergent oscillation. If each cycle is even 5% larger than the one before, then after 10 cycles, the amplitude has grown by more than 60%. After 20 cycles, it has nearly tripled. Starting a demonstration with excessive bank angles did not just look aggressive. It moved the starting point closer to the edge. And with divergent characteristics, the edge was always getting closer whether you could see it or not. Baum initiated the Dutch roll using rudder and aileron. The aircraft began swaying, but the bank angles he used were excessive from the start. Boeing's own training manual specified a desired maximum of 15 degrees of bank and an absolute limit of 25. Simink, the Braniff technical instructor standing behind them in the cockpit, noticed the banks exceeding 25 degrees. He leaned forward and reminded Baum of the limits. Baum acknowledged the reminder, then he ignored it. There may have been an element of showmanship. Baum was 32 years old, a test pilot demonstrating the most advanced commercial aircraft in the world to seasoned airline captains who had never touched a jet. The temptation to impress, to show what the airplane could do, to demonstrate mastery at the edges, is a human weakness that has killed pilots since the beginning of flight. But whatever his motivation, the consequence was that a brand new trainee with zero jet experience was about to be asked to recover from a maneuver that was already beyond the prescribed safety envelope. If you subscribe to this channel, you already know that disregarding safety limits during training is one of the fastest ways to turn a controlled exercise into an uncontrolled emergency. And this instructor was about to prove exactly that. Baum now suggested that he and Burke swap seats so the trainee could experience the recovery from the captain's position. They switched, and Baum initiated the Dutch roll again from the right seat. This time, he did not reduce his inputs, he increased them. Using the controls to their fullest extent, he sent the aircraft into oscillations, with bank angles swinging between 40 and 60 degrees in both directions, 2 to 4 times the absolute maximum allowed by his own company's manual. Inside the cockpit, the 8 men would have felt the aircraft swaying violently, the horizon tilting left, then right, then left again, each swing reaching further than the last. The nose would have been tracing wide arcs across the sky, the wings rolling through angles that made the ground visible out the side windows. For the Braniff pilots, men who had spent their careers in stable propeller aircraft, this would have been unlike anything they had ever experienced. Burke watched several oscillations build before steeling himself for the recovery. The correct technique was specific and counterintuitive. Apply aileron against the direction of the roll motion, not toward wings level. This distinction was critical. If the left wing was down but the aircraft was already rolling back to the right, the pilot had to push the yoke left, into the low wing, to oppose the rightward roll rate. Pushing right would feel correct because the right wing was high, but it would add energy to the oscillation instead of removing it. For a propeller pilot trained on stable aircraft where wings level meant pushing toward the high wing, this was a deeply unnatural response. And Burke had been a pilot for 23 years before this moment. Every instinct he had was wrong for this situation. Burke turned the yoke the wrong way. With the left wing down but rising, he applied right aileron. Instead of opposing the roll, he accelerated it. The right bank angle shot past 90 degrees within seconds. The horizon disappeared beneath them. The Boeing instructor grabbed the controls. Baum's response was fast, too fast. Early 707 pilots had been trained to use sharp, aggressive aileron inputs for Dutch roll recovery. But Baum overcorrected so forcefully that instead of canceling the roll, he completely reversed it. The aircraft snapped back to the left, even harder than it had gone right. He corrected again, too much again, and now the oscillations were no longer Dutch roll. They were pilot-induced oscillations, each one larger than the last, the aircraft whipping from side to side, as the instructor's inputs fell further and further out of phase with the motion of the airplane. The forces on the wings during these reversals were enormous. The engines, the heaviest and densest components hanging beneath the wings, carried tremendous momentum. Each time the roll direction reversed, the pylon fittings had to absorb the force of a multi-ton engine, trying to continue in the direction it was already going. The fittings were designed to fail before the wing did, a deliberate safety measure to prevent the engines from tearing the entire wing structure apart. 3 loud bangs. Engines 1, 2, and 4 separated from the aircraft almost simultaneously. Their thrust levers snapped back to idle and went slack. The control cables severed. 3 Pratt and Whitney JT4A3 turbojets, each generating 13,500 pounds of thrust, tumbled away from the aircraft and fell through the overcast toward the ground below. On the surface near Lake Kavanaugh, witnesses heard the aircraft overhead, but could not see it through the clouds. Then they heard a series of heavy impacts, and then they watched, astonished, as 3 jet engines dropped out of the overcast and crashed into the forest below, with no airplane in sight. Baum finally arrested the oscillations, but when the wings stopped rolling, the aircraft was inverted, nose down. He continued the roll through a full barrel to return to wings level, then pulled out of the dive without further overstressing the airframe. The aircraft was now flying on a single engine, number 3 on the right wing. The FAA inspector went back to assess the damage from the cabin windows. Engines 1 and 4 were gone entirely. Engine 2 had partially separated and was hanging backward, its exhaust pointing up into the flaps. Fires burned in every empty engine bay, fed by fuel from the ruptured feed lines. By the time he returned to the cockpit, Engine 2 had also fallen away. A massive fire was consuming the left wing. The 4 non-cockpit crew, the Braniff flight engineer, the Braniff technical instructor, the second Boeing pilot, and the FAA inspector, made a decision that would save their lives. They left the cockpit and strapped themselves into passenger seats in the tail section, as far from the fire as they could get. The second Braniff captain, Frank Staley, stayed in the cockpit and buckled himself into the observer's jump seat behind the 2 pilots. He chose to stay with his colleagues. That choice would cost him his life. In the tail, the 4 men had a direct view of the escalating catastrophe behind them. The fire had burned a hole clean through the left wing, exposing the internal structure of spars and stringers, like the skeleton of some enormous metal bird. The flaps were destroyed. The left inboard aileron was gone, and with it, control of both outboard ailerons. The 707 used a mechanical linkage, where the outboard ailerons were driven by the inboard ones whenever the flaps were extended. With the left inboard aileron burned away, both outboard ailerons were now useless. The fire had also consumed a 35-square-foot section of the upper wing surface, destroying lift on that side. With only the right inboard aileron and right outboard spoilers still functioning, the crew had roughly 38% of normal roll control. The aircraft was barely flyable. The rudder was still intact, but the hydraulic boost that helped the pilots move it had lost power when 3 generators departed with the engines. Moving the rudder manually through the cables was possible, but required enormous physical force. Meanwhile, the single remaining engine on the right wing was producing asymmetric thrust, pulling the aircraft to the right, while the damaged left wing dragged it to the left and produced far less lift. Baum broke through the cloud base at 4,000 feet and circled near Lake Kavanaugh. Simic suggested ditching in the lake. Baum thought he could find something better and turned down a tributary valley toward the Stillaguamish River. The fire was growing. Melted aluminum ran backward across the fuselage. Pieces of wing fell away in a trail behind the aircraft. An explosion shook the airframe as more fuel vapors ignited. The vertical stabilizer's paint bubbled from the heat. The cabin windows nearest the fire began to crack. As Baum slowed for a forced landing, the reduced airspeed meant less airflow over the remaining control surfaces. Roll authority was fading. If he did not reduce the asymmetric thrust, he would lose lateral control entirely. He shut down engine number 3. The asymmetry eased, but the descent rate increased sharply. It became clear they would not reach the open field ahead. The aircraft clipped treetops at 100 feet, crossed a short clearing, and plowed into more trees. A trunk severed the outboard section of the left wing. The aircraft rolled hard left, shot across the shallow Stillaguamish River at over 45 degrees of bank, and slammed into the far bank. A fireball consumed the forward fuselage. The tail section broke free and slid back into the river, coming to rest in the gravelly shallows with water lapping against the torn fuselage. The 4 men inside, battered but alive, climbed through an escape hatch into the cold October air. They waded through waist-deep water, crawled up the muddy riverbank, and walked to a nearby farm owned by a man named Anton Osler, who had heard the thunderous impact and felt the ground shake beneath his feet. From the farmhouse, they called Boeing. Smaller explosions continued to echo from the crash site, as fuel burned in the wreckage scattered across the riverbed. Debris was spread over a wide area. Several trees were still burning in the dense forest. Rescue crews from Snohomish County arrived to find the forward fuselage completely destroyed by impact and fire. Russell Baum, John Burke, Frank Staley, and flight engineer George Hagan were killed instantly when the forward section broke apart on impact. Burke had 23,000 hours. Staley had 20,000. Between them, they had nearly half a century of flying experience. None of it had been in a jet. Baum, the instructor who had pushed the aircraft past its limits, had 369 hours on the 707. He was 32 years old. The Civil Aeronautics Board investigation was direct in its finding. The probable cause was structural failure of the engine pylons due to excessive control inputs during an improper Dutch roll recovery that had exceeded the prescribed bank angle limits. The instructor had initiated the maneuver well beyond Boeing's own guidelines. The trainee had recovered incorrectly, and the instructor's correction had induced pilot oscillations violent enough to tear the airplane apart. But the investigation also asked the harder question: why was this training conducted this way in the first place? The 707's slightly divergent Dutch roll characteristic meant that a botched demonstration could escalate faster than a stable design would allow. The early yaw damper's interference with the rudder pedals forced pilots to turn it off precisely when Dutch roll was most dangerous, during low-speed operations with flaps extended. And the training protocol placed brand new jet students, men with decades of propeller experience but zero jet hours, directly into the aircraft's most vulnerable flight regime on their very first day. This was not an isolated event. Just 2 months earlier, in August 1959, an American Airlines 707 had crashed during a training flight at Calverton, New York, killing 5 crew members. That accident also involved an unintentional rolling maneuver at insufficient altitude. The jet age was advancing faster than the industry's ability to train for it safely. The aircraft existed, the simulators did not. And the gap between what these airplanes could do and what their pilots understood about them was being closed, flight by flight, sometimes at terrible cost. The investigation also noted that the instructor, despite being qualified on paper, had only 369 hours on the 707. That was not unreasonable for the era, given that the aircraft had only been in service for a year. But it meant that the person responsible for teaching others the aircraft's limits was himself still learning where those limits were. And on this day, he found them. Boeing responded with changes that would reshape the 707 and influence jet design for decades. The vertical stabilizer was enlarged, and a ventral fin was added beneath the tail, improving directional stability enough to reduce the 707's Dutch roll divergence significantly. A new yaw damper was developed that operated without moving the rudder pedals, eliminating the need to ever turn it off during any phase of flight. An independent backup hydraulic system for the rudder was added, one that would function even without main electrical power. And the bank angle limits for Dutch roll training were re-emphasized across the entire fleet. The engine pylon fuse design, the deliberate weak point that allowed engines to separate before they could destroy the wing, had functioned exactly as intended. The engines broke away, the wing remained attached. The aircraft, though crippled and burning, stayed in one piece long enough for 4 men to survive. That same design philosophy persists on every underwing engine transport aircraft flying today. It was validated in fire over Washington State by 3 Pratt and Whitney turbojets that fell through the clouds and landed in a forest where no engine had any business being. It would take more than 4 decades before another major accident demonstrated the same principle in reverse. In 2001, American Airlines Flight 587 departed New York and encountered wake turbulence. The first officer made repeated aggressive rudder inputs that overloaded the vertical stabilizer until it separated entirely. The tail broke off. The aircraft crashed in Queens, killing all 260 people on board. Different control surface. Same fundamental lesson. Repeated large opposing inputs generate structural loads that build faster than human intuition can predict. The airframe will fail before the pilot realizes what he is doing to it. Later versions of the 707 and every swept-wing transport jet that followed incorporated these lessons. The yaw damper became a system that pilots never had to think about, running quietly in the background for the entire flight. Dutch roll went from a daily concern to a theoretical concept studied for exams, but almost never encountered in practice. And flight simulators, which would arrive within a decade, would eventually make training flights like this one unnecessary entirely. On October 19, 1959, a brand new Boeing 707 took off from Seattle, with 8 men on board for a training flight. Its yaw damper was turned off deliberately so that a trainee could learn what happened without it. The instructor pushed the aircraft past its published limits. The trainee turned the controls the wrong way. The instructor overcorrected, and 3 engines fell out of the sky. The yaw damper switch that started it all was 6 inches from the instructor's hand the entire time. Turning it back on would have ended the Dutch roll in seconds. It was never touched. Today, the yaw dampers on every commercial jet in the sky run silently from takeoff to touchdown. They do not interfere with the rudder pedals. They do not need to be turned off. Pilots rarely think about them at all. And Dutch roll, the phenomenon that once required first-day training in a real aircraft with real consequences, is now something that airline pilots study for a written exam and almost never experience in flight. The 707's vertical stabilizer grew larger. The ventral fin appeared beneath the tail. The oscillations that killed 4 men over Washington state became a footnote in an aerodynamics textbook. The airplane learned. The industry learned. The cost of that education was paid in the Stillaguamish River. If this story stayed with you, consider subscribing so you do not miss what comes next. Every one of these accidents left a mark on the aircraft we fly today, and some of those marks are still visible if you know where to look. In our next video, we will look at a crew that faced an emergency no simulator had ever prepared them for. Not because the scenario was unimaginable, but because the people who designed the training decided it was too unlikely to bother with.